guys. Okay, so for the rest of the year, which really isn't that much, I'm splitting y'all where AP is going to keep working on their AP stuff, where y'all are going to finish Module 14 after spring break. You'll take a test on Module 14, and then I'm going to go ahead and start y'all reviewing for your final exam, whether you're taking it or not. I guess Rachel's the only one that would qualify for exempting it. Anyway, we're all gonna just do our own review of everything of the semester and keep y'all separate from what AP is doing, okay? All right, so the second part of Module 14 is capacitors, okay? If you want, you can do the, it's an easy at-home lab of the capacitors with they use two styrofoam plates. So if y'all want to look at that lab, if you want to do it, you can make a little video showing me that you did it. I'll give you extra credit. It's up to you. Anyway, so capacitors. Capacitors is a device that stores charge. Okay. And there's many different types and there's many different uses for them. The one that I was just talking about, and it's called the parallel plate capacitor. And the parallel plate capacitor, it has two conductive plates that are obviously parallel to each other. So they're gonna look like this. So these are two plates, okay? They're separated by a very small distance. This, I'm showing a pretty big gap there, but it's normally a small distance. And the plates are full of opposite charges, okay? So, like this plate would have negative charges, and this one, the bottom plate, would have positive charges. Okay. All right. So, like I said, there's these are the metal plates. All right, and they're connected by wires, because they're going to be in a type of circuit. And then we have this, separation distance. All right, so the opposite charges are going to attract each other, but they're not free to move. Those positive charges are stuck on the positive plate. The negatives are stuck on the negative plate, okay? And then the substance between the two is an insulator. So you can put a piece of cardboard, that's what I'm saying, there's small distance, because you'd have a piece of cardboard sandwiched between there, or cloth, or something like that, or glass is another one. Anyway, so like I said, you've got something sitting between there. Sometimes it can be just air as well. So the total charge on each of the plates has to be the same. So if we have 5 coulombs negative, we also have 5 coulombs positive, okay? And so if you do that experiment at home, the styrofoam plate is basically the insulator, okay? And so we have this term dielectric, and that is an insulator, meaning something besides air, okay? All right, so like I said, the capacitor stores the charge, and so one side is positive, one side is negative, and in the styrofoam plate lab, when you go to touch, you're gonna put a what's the word? Paper clip. Put a paper clip on there, and you touch the paper clip. You're gonna get shocked. Very teeny tiny. This isn't like, I mean, he wouldn't have put this in the book if you're gonna have something major happen. But you will, you know, and it is less than, you know, normal shocking feeling that you get when touching stuff. It's very, very little. So if you're game for it. And what's happening when you touch that strip, you're connecting the two sides to one another, okay? And so that charge flows through your body. All right. The electric field of a parallel plate capacitor is going to be, you know, these positive charges going to the negative side. Okay, so that field is going to stay contained right there. All right, to calculate the electric potential, we have of a capacitor. All right, so V is our electric potential. Q is the total positive charge stored. And then the CQ is the capacitance. Okay, so here's our equation. All right, capacitance that is how much charge a capacitor can hold at a given voltage. Okay, the capacitance depends on the size of plates and the separation distance. All right, not sure if I'm still in the camera or not. Okay, so if you have large plates, okay, you've got lots of room, and you're going to have a high capacitance. If the separation distance is large, then the charges are not going to attract as well, and you're going to have a low capacitance. Okay, so the bigger the plates increases the capacitance. The smaller the distance will also increase. Bigger distance, it's going to weaken it. All right, so the units of capacitance is coulombs per volt, and that is also known as a farad. Okay. All right, so we're going to do an example. All right, so we're going to have a 3.2 times 10 to the negative 6 farad capacitor. And it is charged, so there is 4.5 millicoulombs. All right, and we want to know what is electric potential. So we're just going to use our equation right here. We've got volts is Q, which is our 4.5, that's millicoulombs. So we make sure we change that into coulombs. And then our farads for our capacitance. All right. Calculating that out, you should get 1406 volts. Okay, so a capacitor, one of the reasons we use it is because it can, it creates an electric potential that is localized, you know, because like so we've got our capacitor here, and it's, the electric potential stays within that area of the capacitor, okay? Because the electric field, you know, as we showed earlier, it is confined to those plates. It's not going to go outside of that the capacitor at all. All right, so if a capacitor has an electric potential of 10 volts, then the potential difference between the positive plate and the negative plate is 10 volts. All right, so there's our positive plate, and our negative plate. All right, so the electric potential going from positive to negative is 10 volts, okay? So a free moving charge would experience a change in the, of 10 volts in the, as it traveled from one plate to the other in the capacitor, okay? All right. All right, so just important to know, when a particle moves from the negative plate to the positive plate, it gets an increase in electric potential. And then when a particle moves from positive to the negative, it gets a decrease in electric potential. Alright, so we use capacitors basically to accelerate the charged particles. Okay, if you put a positive charge next to the positive plate, it's going to be attracted to the negative plate, and it's going to accelerate towards it. And so the electric potential determines how fast the charge is going to move from one plate to the other. Okay. So the greater the electric potential, or say the greater the change in electric potential, means the greater the change in potential energy, which of course is then going to mean a greater change in kinetic energy. Okay, and then from kinetic energy we would get the speed, greater velocity. Okay, so all those things just compound on each other. Increase electric potential will increase the potential energy, which will increase the kinetic energy, which will increase the velocity. Okay. All right. So we're going to do one more example. All right, we have a free moving electron. It has a mass of 9.1 times 10 to the negative 31 kilograms. Its charge is negative 1.6 times 10 to the negative 19 coulombs. And it is traveling from the negative plate of 2.5 times 10 to the 6 farads to the positive plate. And we want to know how fast will it be moving. And then the capacitor has a 0.87 milli coulomb stored charge. Okay. Yep. All right. So we're going to start with our capacitance equation, Q over CQ. All right, so our charge, the capacitor charge is the 0.87 millicoulombs. Okay, so make sure you convert that. The capacitance is the 2.5 times 10 to the negative 6. Alright, so we calculate that and we're going to get that our electric potential is 348 volts. Alright, since we're going from the negative plate to the positive plate, then we know that that is an increase. Okay, we're changing our electric potential as an increase. So we know that that's going to be positive. If we went from positive to negative, it would have been a decrease. Alright, so if you remember, change in potential energy is Q change in electric potential. Alright, so that is our charge here, because we're looking to see what that electron is doing. And that's times, 348. Okay, so that is going to give us negative 5.568 times 10 to the negative 17. That'll be joules. Okay, so if potential energy is going down, potential energy is decreasing, then we know kinetic energy is increasing. So we have a positive 5.568 to the negative 17 joules of kinetic energy. All right, then that is going to equal 1/2 mv squared. We're going to put our mass in from up there. 9.1 times 10 to the negative 31 v squared 1/2. Okay. All right, so we divide this over to there, and make sure you square root your answer, because you have v squared, and so then our velocity is going to come out to be 1.1 times 10 to the 7th meters per second. All right, so y'all make sure you try this yourself and make sure you get the right answer there. And again, if you want some extra credit, shoot me a little video or pictures of doing the little styrofoam plate capacitor experiment. It's in your book. And so then you're going to do the second part of the on your own and practice problems. and then also complete the review and extra practice like we normally do, okay? All right, so have a good week and have a good spring break, and just a few more weeks left after that. Alrighty, bye-bye.